right. Hello, everybody. We are live. I have my Discord pulled up. All right, let's go ahead and let the chat know, or let the Discord know we are live. All right. I hope everyone's having a wonderful day so far. My name is Michael. Welcome back. Today we are jumping back into studying, and not gonna lie, you guys, I'm pretty gassed today. It was a long day at work, and just had a late dinner, and so I'm pretty tired. And I'm not as efficient when I'm tired, that's for sure. But I'll try my best to be present and learn. I'm not gonna promise anything. I might struggle today. I'm pretty tired. Jeremy, thanks. I appreciate you being here. Actually, that message is very kind. Actually, Jeremy, I was struggling to join today. I'm not gonna lie. I'm just like everybody else. I'm just had to really talk myself into getting on the stream, and I was making excuses, and I'm just tired today. Work, and it's been doing these streams for back to back every day for the past like week, or almost a little bit more than that, maybe. Yeah, so I'm pretty good. But building endurance, let's say. What doesn't kill you makes you stronger. As cringy as that is. I appreciate you coming in, Jeremy. Thank you. Okay, so we are back studying Python here. Oops, move my books out of the way. Put that dog hair out of my desk. Jeez. Where's my dog at? Sky! Come here. Come on up. Gotta get my dog in here to keep me some company. What the heck? I can never talk on stream. I always get so razzled. I don't know. I don't talk much. I'm pretty quiet. So, all right, let's get started here. Sorry, I'm getting all situated. Get my keys and my badge off. All right. As you can tell, I kind of just rolled in and got dinner, and yeah, so we are back doing Python, data structures and algorithms in Python. I wanted to do a brief review about what we went over yesterday. So Zaid Ahmed, thank you so much for coming and leaving a message. I appreciate you being here. How are you doing? I appreciate you so much. Thank you. So yeah, we're back in chapter 3. We started chapter 3 last stream, which was algorithm analysis. And so I have a running definitions section here. We defined what a data structure was, just a systematic way of organizing data and accessing it, right? And an algorithm is like step-by-step instructions that are executed with some sort of finite or determinable runtime. It's not like infinite. Algorithms, I guess. In this, with a finite amount time means like a finite time means like a certain amount, correct? Typically, or constant duration, that clear beginning and end. Yes. So under this like circumstance, infinite, loops and things like that aren't considered algorithms, right? Because they have no kind of end. So, yeah. Running time. Doing good. I started learning Python last month, taking Python course on Udemy. That's really awesome. I have a colleague, actually. He graduated from a state school, not the one that I went to. We actually went to kind of like a camp in the summertime together and have stayed in touch. And he actually has a degree in neuroscience, and he learned to program as well. Taught himself a few years back, and he taught himself through Udemy courses on about web dev and stuff. So yeah, he kind of pivoted and did that whole thing a couple years ago. So really cool, awesome. Do you like it so far, Zayed? I appreciate you interacting here on the chat. You make it really fun. You guys make it really fun to stream. You guys are asking questions and talking to me. Okay, so then we have running time, which just is the measure of natural quote unquote goodness and of a of a algorithm in a sense. We want these to run as fast as possible. And we learned later in the text that we want to run to account for the worst case scenario to happen in an algorithm because an algorithm can mul- different the same algorithm can take varying amounts of time uh, to run. So you plan for the worst case scenario or code for the or optimize for the worst case scenario. That way you just dot all your i's and cross your t's. um, there's no you know un I don't know. I'm struggling. I'm tired, guys. It's wake up, wake up. We gotta learn. So we learned this funky word, which is a benchmark time for an algorithm. I want to look it up one more time again here and see what Jippity tells me in simple terms, because I still don't really understand this one quite fully. An epoch is a specific moment in time used as a starting point for measuring or organizing other moments. It's like marking day one and counting from there, meaning an epoch depends on the context. An epoch in history. Okay, so it's just a benchmark time um, start for an algorithm, pretty much. Like, got you. Interesting. We have primitive operations. So these are just like um, bare bones operations that the computer can run, such as functions, um, addition, multiplication, searching through some data, maybe like indexing, um, variables, things like that. I don't know, maybe not variables, but like I guess that may be encompassed inside of primitive function operation, a primitive operation. But yeah, it's like math comparisons, data access, comparison variables. Yeah, equal to control flow, looping function calls, right? So then we went into experimental studies where we talked about the time module and how this provided us two functions, time and clock, which we could use to set epochs or I'm gonna I want to call this epochs for some reason. Epochs for we can set epochs within the code using their allotted functions and kind of record the time at which that function was called and then within the system, and then we can take the difference of those points to find an overall elapsed time. And but this has some nuances with it. It's not perfect because elapsed time is dependent on and is affected by other processes running on the computer simultaneously. So just like your operating system has some systems going on in the background to connect to your monitors and for drivers and things like that. Bluetooth. I'm guessing, and these probably vary in certain circumstances, and I might not be perfect. I'm trying my best here to give examples off the top of my head, but again, I'm trying to solidify this concept and learn by going back through and before we start today. So, and then we got clock. This one measures the number of CPU cycles that the software goes, not the hardware goes through itself. So that makes it hardware dependent, which has some nuances. So we learned about the time it module. So I need to look this up. Time it module. The time it module in Python is used to measure the execution time of small code snippets. It's a reliable way to time code because it minimizes variations due to background processes or other factors. Precision. Designed for accurate timing of small bits of Python code. Repetition executes the code multiple times to reduce noise and provide a robust average. Convenience works with both one-liners and multi-liners. Interesting. So I'm going to go here really quick. I'm going to Command F and look up the time it. Okay, so it's first brought up right here. So Python includes a more advanced module named TimeIt to help automate such evaluations with repetition to count such variance among trials, which to help automate such evaluations. What evaluations? This can be determined using clock. No. Just the elapsed time then with different evaluations over and over again. Okay, so uh, automate time evaluations with repetition to account for variance among trials. Okay, so we'll leave it at that for now. Let's get caught up with the chat here. Hey, you guys, I appreciate you joining for this evening. I'm not gonna lie, I'm pretty gassed for today. It's a long day of work making solutions, getting ready for my next product I'm building. You know, I kind of make solutions and then I put those solutions into a big solutions and then I put that solution into bigger solutions and I test them and I with math and on the back end, and it's basically chemistry in a nutshell. Just kind of like advanced cooking in a way. Um, yeah, so I'm pretty tired. I was on my feet quite a bit in the lab today, and didn't get out till late. And anyways, bear with me here. I'm trying to get back into it. But I appreciate you guys joining me. Like truly, thank you so much. We crossed over 200 subscribers, by the way. So huge thank you. We talked about that. We did that in the last stream. So honestly, I can't believe that. Like, it's just unbelievable that you guys have blessed me with your time, and it's crazy. So thank you so much. Okay. So we then learned about primitive counting primitive operations. So this is where we started diving into some more elaborate stuff. Counting primitive operations. So to analyze the running time of an algorithm without performing experiments, we perform analysis directly on high-level description of the algorithm. So you can count these primitive operations that we talked about earlier. Math, comparisons, data access, control flow. You can count them, and then that being said, it provides some. So it's character f of so some function of n input size, right? Um, you put in some input size into the algorithm, right? You provide it some input, and to perform these operations on, and these primitive operations, and they overall like increase that runtime in certain ways, right? Now this function associated with this algorithm, right? This represents the time or the value of time. I'm assuming of the algorithm as a whole, function of n. Of the count of primitive operations, from my understanding as we refreshed from yesterday. Right, because then we have for constant functions, which were probably one output, and then we talked about log as well, so we'll get there exactly. Vansh, I appreciate you coming in. Thank you so much. Yes, I put the tags on like you said, so thank you for the recommendation. I threw those in there. Thank you. Um, okay. Oh, we got some. Sorry, I'm getting behind on chats here. My bad. My bad. I started learning Python last month. Okay, we talked about that one. You're killing it, dude. Keep it up the good work. I'm a CS major, by the way. Varun, is it Varun? I'm really sorry if I pronounced that incorrectly. If you could give me a pronunciation, I'd love that. I'm really bad at pronouncing stuff. As you can see, I stutter quite a bit just talking to you guys. I don't really talk aloud a lot, so it's kind of new for me. Anyway, but it's good to practice. Your CS major, which is really interesting. What do you like about it? Do you think it's pretty hard or challenging? I graduated back in 2021, not as a CS major, but in the STEM field. I have a Bachelor of Science in human biology and a minor in chemistry. And I'm currently working in the professional field right now in that environment. But thank you so much for joining and leaving a message. I appreciate you. All right. It's good to learn how to code. Feels good when you're in a bunch of trial and error and the code executes as it's supposed to. Yes, love that. Juan, hi. Why are you learning Python? I'm interested in learning listening to your reasons. Yeah, like I said earlier, I kind of talk about this on my streams. I'm sorry if I repeat myself, guys. Just bear with me because I like to answer people's questions. I'll be quick. I like to I do a lot of, chemical calculations by hand, and that just sparked me wanting to figure out if I could have a computer do it for me, in my current like chemistry field. And I haven't actually solved that problem yet. I've been diving into more learning and projects that I'm working on, but um, eventually maybe I'll turn back into the chemistry, and that'd be kind of interesting to take that. I just want to get really confident first before I dive into something I am more knowledgeable about. I want to kind of match my level, and be able to be fluent in it as well. So, um, yeah, and that just like sparked this whole learning. I started with CS50P, the Harvard course. I did that on a very, very part time for about 3 months, and then starting in September, I really started grinding away at the streams and learning and reading these books. And I did Python Crash Course. I read all that book live on stream here and did the problems live on stream. And now we're doing this one. And yeah, but we got to keep moving here, you guys. We talk a lot, talk too much. Some people might not like it. Like, get to the stuff. Toast, thanks so much for coming in here. Appreciate you seeing again. Appreciate seeing you again. Man, I am struggling talking today, guys. I struggle to talk every day. It seems like you gotta stop smiling. It makes it hard. Okay, let's get moving here. So, like yesterday, we learned about the constant function. So this just means that no matter the input or the input size into our algorithm, the we always are provided a default value of whatever the C is provided, right? It's overridden. No, it's independent of our input size. So then we talked about logarithm functions, and this is where we got into the kind of nitty gritty here. And it really started to dive in quick, giving us like logarithm rules, which some people in the chat said we should kind of take these with a grain of salt. We don't really need to know them per se. It's obviously nice to know them, but they're not super necessary unless we're maybe performing some mathematical operations using these logs. Obviously, it even gives you calculator equivalents, so that can be my only, kind of prediction into why I would provide this. But we also, I kind of wanted to talk about this. So we just need to say, like, let's just say we need to give a definition for the logarithm function, right? Um, so b is equal to base, right? The most common base for a logarithm function in computer science is 2. Most common base for computer science is b is equal to 2. For like a binary, right? And because most common operation in algorithms is to repeatedly divide an input by half. So then by convention, log of n is equal to log base 2 of n, right? So this is different from most calculators with log base 10 for computer science. Okay. You guys are answering the questions before me. Good job. I've seemed to be really honing in the information here that Right, so this is the data structures and algorithms in Python. I should probably like put like maybe a text thing on the screen to show that this is such, because I get that question quite a bit. I think that this font is quite small and you guys just maybe can't read it up here. Okay. Yes, this is CS50P, or sorry, this is data structures and algorithms in Python. If you want, I have a Discord where I provide the PDF. You can also just look it up online, but in my Discord, I just have a conglomerate of all my study resources in one location for you guys. Completely free, linked below. Um, for logs, it seems like you're reviewing. You should also consider what happens to an algorithm in log time. Yes, so I think we're getting there. We have so I think this is just kind of introducing the function, and then how I think we're gonna see how it applies to the algorithm itself. But this is just kind of defining the introducing the function in itself. So one of the interesting sometimes ubiquitous the presence of a logarithm function for some constant b greater than one. So we need to say that for constant b greater than one. Um, right, and so someone in the chat said a good way to think about this is to say, um, right, for we can do like an example here and say, let's do how we have it formatted above. Example is, so what do we say before? If we have an example of like, um, what gives me, like, is it log base 2 of n is equal to like 4? So doesn't this just tell you, what was the little trick we were talking about earlier, you guys? Mohammed, thank you for the kind words. I appreciate that. Yeah, I cut off my hair. It's got a little bit of a different style now. Appreciate the kind words, though. Yeah, thank you so much. So there was that little trick. Basically, we're trying to say that the 2 to the power of what value equals 4. Is that what you're saying? Is this essentially base time power of n is equal to 4? Okay, here we go. So log base 3 of n is equal to 27, or, okay, here we go. Thank you so much, Vance. So log under base 3 of n is equal to 27. So this also can represent 3 to the power of x is equal to 27. Perfect. So now tell me this, is x different from log n in any way? Now, or does the answer, is that some sort of, like we talked about here in like these right here, you get what I'm trying to say, like base, so it's 1 out front. Okay, got you. It's n instead of x, so that would explain the question. So, okay, sweet. Thank you so much. So essentially, when you have a log with a base, with a multiplied by some function of n, is you have some value that actually equals the outputs, right? And we need to solve for this value. Now this might seem arbitrary, but maybe we'll use this. It's the same as essentially saying the base to what power is equal to the answer, and solve for the power. Um, Now, exactly how do we do this again in algebra? It's been a long time, folks. Obviously, you'd have to, if you were to, you could, how do you remove an exponent from, or a variable out of the exponent's place in algebra? Forgot about that rule. No, these just deal with the logs, really. Moving, factoring a variable out of exponent. You would just root. You could root using the law of exponents. No, that's not my answer I'm looking for. Let's just kind of, refactor it. No, it's 27 to the power of 1 over n is equal to 3. So if you had like 3 to the power of, I'm trying to, essentially, it might just seem arbitrary, but how would you like solve that by like hand, essentially? We know it's 3, right? 27 expresses a power of 3. Substitute. Oh, so you just reduce it down like that? That seems kind of like a cheap way to do it. Okay. So it took 27 division or steps by 3 to reduce n to 1. 27 divisions. So like Toast said, 27 divided by 3 equals 9, divided by 3 equals 3, divided by 3 is 3 times. So it's like what we talked about here. Okay, yeah, they add in a bunch of stuff into this log stuff. And to be honest, guys, I was not the best, as you can probably tell, at logarithms in my calculus and in my in college. I it was my freshman year. It was a long time ago. Even just general math, I'm still pretty rusty at. Now, dimensional analysis and chemistry, and I can give you that all day long. But okay, so log base 64 is 3 because 64 divided by the base gets to 1 3 times. Okay, so you are sent you how many times? So how let's rephrase this into words. How many times can n be divided by 3 to equal, that provides the less than or equal to 1, though? This is just the ceiling. So it kind of is a calculus, but it's an approximation, that's right, in some certain circumstances. Loki, the book is trying to confuse you. I feel like that is the case here. I feel like it's trying to get you way into these nuances. Maybe we should just kind of continue here and move on. So, well, we do need to kind of add this part, though. This seems pretty important. So, computing logarithm function exactly for any integer n solves use of calculus, but we can use approximation. In particular, we can easily compute the smallest integer greater than or equal to log nb by its so-called ceiling. For positive integer n, this value is equal to the number of times we can divide n by b before we get to a number less than or equal to 1. How many times can we divide n by 3 27, right? Oop, whoops, let's not go over a water bottle. Ceilings round to the upper number. So we do need to add that in. I feel like that's important. So let's see, ceiling is the uh, ugh, a formal definition for that's kind of hard. I feel like we're kind of getting. I feel like we need to move on though. It's kind of doing us no good to kind of sit here, and pitter patter over this. So let's kind of move on here, guys. Ceiling is important when dealing with problems that involve dividing or partitioning numbers. Or partitioning numbers. Gotcha. Ceiling rounds to the upper whole number, so 0.9 equals 1, 0.2 is 1, 0.3 equals 1. Okay. It always rounds up to the whole number. So ceiling, um, a rounding, um, rounding. So would you round down though ever? You always round up? Rounding up. Rounding up of integers. So like 0.2 would become 1. 0.7 would become 1. Seal equals round up, floor equals round down. Okay, thank you. Kerwin, yes, I trimmed my hair. Thank you. I appreciate the kind words. Awesome. Okay, let's move on here, you guys. We need to kind of keep going, just for the stream's sake and for my own sanity's sake. Wouldn't it be rounding up of floating point numbers because integers are whole numbers? Oh, yeah. Rounding up to the nearest whole number. We'll just say that. Okay. Cool. So now we have what's called a linear function. Now these ones are, I'll knock on wood here, but these ones I think are the easy ones. Yeah, another simple yet important function is the linear function. F of n is equal to n. It's equal to the input size in a linear correlation, right? That is given an input value. Why would they throw the log at you first? They should have thrown this one at you. That is given an input value n. The linear function f assigns a value n itself. Assigns the value n itself. This function arises in logarithm analysis at any time we have to do a single basic operation for each of n elements. For example, comparing a number x to each element of a sequence n will require n comparisons. The linear function also represents the best running time we can hope to achieve for any algorithm that processes each of n objects that are not already in the computer's memory, because reading in n objects already requires n operations. Okay. So in some circumstances, if you have objects that are like not in the memory, in some cases the best you can do is perform in a linear function of speed, right? Representation, or however you would put it. because you rely on processing all of that new data, um, however the size. So I'm going to take this right here. Function that when given an input value and the linear function f assigns the value n itself. No, I don't like all those whatever commas. Okay, it's fine. Yeah, we looked in the log for way too long. Exactly. We had to move on. We had to go. We had to leave it behind. I liked processing it though, and I wanted to get my head around it, you know. But sometimes you got to just put your nose forward and come back to some stuff if it's still not sticking entirely. Obviously, we're getting some of it. We're getting there, but we still got a lot to go. They are going in order from fastest to slowest. Okay, so a constant function is. Why would a constant function be the fastest function? Just because you have a known output every single time. It's not variable at anything. It's always that, no matter what, um, for any size input, obviously, right? If you had a million inputs, no matter what, and you had c equals 5, you'd still get 5, right? Okay. Um, it's the speed of worst case of each. Okay. It's always same runtime, not relying on input size. Yes, correct. Regardless of input size. Perfect. Sweet. See, we're getting somewhere, guys. We are getting it. Little by little. It's possible. Okay. Moving on. So linear function in itself. So this function basic elements n, for example, comparing a number of x if value itself. Um, I'm going to copy this part right here. Oh, that was terrible formatting. Okay. The linear function also represents the best running time we can hope to achieve for any algorithm that processes each of n objects that are not already in the computer's memory. Okay, I feel like that was a good one to add. So, cool. Let's move on. Number 4. Vance says it's always on runtime. Toast says regardless of input size. Toast, I wish YouTube had better chat experience. To be honest, I bet it's not all YouTube chat. I'm just pretty slow at getting these responses out. I often get lost in the chat. Um, like it makes it kind of. I guess it could be better. It makes it hard to kind of sort through and read. Um, cool. So now we're going to move on to n log n function. So the next function we discuss in this section is the n log n function. Right? So this is f of n is equal to the n log of n. Now, was this a refactoring of one of these rules up here? Where did I see that you brought out something out front here? Oh, it was when it was being powered. So is this essentially the same as saying log to the of n to the power of n? as well. You know what I mean? Due to this rule. This looks pretty similar to me. Now A and C are different here, are different here, but n and n, but is this not just n to the power of n as well? Or does that assume that these have to be different? Okay, let's keep going. Uh, n log n. That is the function that assigns to an input value n the value of n times the logarithm base 2 of n. Right? So for every input, for the input size log base 2 of n by n times, by the input size times. This function assigns an input value n the value of n times the logarithm base 2 of n. This function grows a little more rapidly than the linear function and a lot less rapidly than the quadratic function. Therefore, we would greatly prefer an algorithm with a running time that is proportional to n log n than one with quadratic running time. We will see several important algorithms that exhibit a running time proportional to n log n function. For example, the fastest possible algorithms for sorting n arbitrary values require time proportional to n log n. Hold on, my phone's ringing. You guys give me a second. All right, we're back. Sorry, guys. My girlfriend was calling me. Oh. Okay, so I'm not fully understanding the n log n function. Um, n log n grows towards infinity logarithmically. We are starting to get into bad time complexity. Horrible is up next. Okay. So what exactly, I feel like this wording makes it kind of difficult, n times log base 2 n over and over again. So we obviously have our input size is being used. So the function dependent on our input size that runs for the log of our log base 2 of our input size is multiplied by our input size again. So for every, now is this just that one instance of the total input size? Or is this just, is that make sense? Like, not total input size, is this just one instance of input? Or is this for the entire n value? If that makes any sense. I might be thinking about this in a wrong way, but, or I might be thinking about it kind of creatively. What do you guys think? Hopefully, chime in. Give me the corrections. Let's see. Simply explain n log n to me. Let's see how the almighty orb does. Right, is a way to describe time complexity of an algorithm. It means that the time the algorithm takes grows proportionally to the size of the input n multiplied by the logarithm of that n. Okay, yeah, we understand that. Key points: n is the number of items in the input, right? Log n, a function that grows much slower than n, roughly describing how many times you can divide n in half before getting to 1. Okay, and so if you're multiplying by n again, are you essentially getting even more slower? Or would, because if like I'm thinking of the example of base 3, right? We did up here, n log base 2 327. You want to plot them? Okay, let's plot them. Let's plot them up. Desmos. Oh, whoops. Hey Anthony, welcome back. I appreciate you coming in. You're always a great help in these streams. So n log n. Okay. So this is base 10. Let's see base 2. Does it matter if I do f of n at y equals? No, it's the same function. Okay, so this one, interesting. So you have to have one input. You can't have less than one input, right? That's what that means, I'm assuming, right? If you have less than one input, you get a negative value. The log doesn't work, right? So you have to have an input value of 1 at the very least. And then at 2, you have an input value of 2. At 3, there. 2, 3. Now let me plot just f of n is equal to n, linear curve or linear function. So this function, they intersect at this point. So what does that tell us at 2 and 2? What does the crossing over of the two functions tell us? Like an inflection point of where the log becomes less efficient, right? It starts becoming slower because it's processing less inputs and taking more time. Or is x-axis the time, or is y-axis the inputs? F of n. So x-axis is the inputs, y-axis is the time. So for more inputs, as our inputs increase on the x-axis, right, it starts taking more time for more inputs on the n log n. Dude, I think I'm getting this. Am I not? Am I not getting this? Am I not getting this? What? Am I not getting this right now? I feel like I am. That's so cool. Okay, let's go to the chat here. I'm missing your guys' chat. Sorry. N log n grows towards infinity logarithmically. Yes. When we are starting to get, okay, yes, you should plot these functions. Yes, okay. Remember to do what? Okay, got you. Typically, an input will always start with 1 anyways. You can't have half an input, and having no input means the algorithm will not have anything to calculate, so it just exists. Okay, got you. You can see how the n log n rapidly grows compared to the linear function. Yes, y-axis time. As input grows, time increases faster with n log n versus n. You can get away with bad algorithms with small inputs. This all gets important with large inputs. Just, you are totally getting it. Okay, cool. So as you can see, as we scroll up in our graph here, if we scroll out here, our n log n function, as our inputs increase, right? So let's plot a y graph here. So let's do a couple, and let's do y equals 100. Right, let's scroll out. Okay, so we have these two input sizes here, or these two timestamps, right? And at what time? So I'm gonna try to get all these points here. No, it had to be x equals. Sorry. Right, because that's our input size. So at x equals 100, okay, this is a good example, right? So at x equals 100 right here, you can't really tell. You can kind of tell there's some separation between, but it's fairly small. Like these inflection points, you can, with these smaller inputs, but as you start increasing this input, right, as we start getting larger x values, this linear function is still is 1-to-1 for every input value, right? But our logarithmic function is taking now 664.38 as our output, 0.39 as our output. So it's taking almost over six times longer at a x equals 100 for this example. Interesting. Okay, this really helped. Thank you for suggesting to graph these. This really, really, really helped. Honestly, truly, truly, truly. So I'm curious to see then if I plot log here compared to the linear function. The log definitely goes faster, obviously, as inputs increase. You almost kind of asymptote at what y value. Like, what y value is this? Like 8? 6? Interesting. Okay. Let's keep going, people. Let's keep going. So we will see several important algorithms that exhibit a running time proportional to the n log n function. For example, the fastest possible algorithms for sorting n arbitrary values will require time proportional to n log n. The quadratic function. Another function that appears often in algorithm analysis is the quadratic function. Oh, we didn't really write anything here. Not good. We'll come back. Okay, so this is, f of n squared equals n to the power of 2, right? Okay, your favorite, Vanch. Okay, let's see what it's about. That is, given an input value n, the function f assigns the product of n with itself, in other words, n squared. Given an input value of n, the function assigns the product of n with itself. Okay, the product n times n, or n squared. The main reason why the quadratic function appears in the analysis of algorithms is that there are many algorithms that have nested loops, where the inner loop performs a linear number of operations and the outer loop is performed a linear number of times. Thus, in such cases, the algorithms performed n times n, or n squared operations. So when you have two linear functions together in some sort of nested loop, that's very interesting. How did people figure this out? Like, it's so mind blowing. Like that we're learning it, but people had to have figured. It's just insane. Like oh my gosh. Okay. I'm going to take this part. Um, function that when given an input value of n, the function f assigns the product of n with itself. Right? Cool. All right. Welcome back, Toast. Appreciate you coming back. We missed you. For I in range n, for index in range n is constant time when you have, or for integer in range n is constant time. So when you have for I in range n inside another for j in range n, and now it's n squared. Correct me if I'm wrong, guys. No, that sounds exactly like the interpretation when you have two nested for loops performing some operations over n data, right? Yeah. The easiest explanation of n squared operation would be to imagine transversing a matrix that has n rows and n columns. Naturally, you're going to perform n squared operations to traverse this. Yeah, linear time is exactly what you meant, not constant. Linear time. Advantage. I follow what you're saying. No, all good. Linear, not constant. Because it's two linear functions together. Because it's the linear function is f of n is equal to n, right? Not f of n. This isn't c squared, constant squared. Whoa. Okay. So I wanted to take this part. So algorithms that have nested for loops where the inner loop. So we'll do the example here, right? And we'll use your example for I in range n. Perfect. Cool, so let's keep moving here. The nested loops and the quadratic function. The quadratic function can also arise in the context of nested loops, where the first iteration of a loop uses one operation and the second uses two operations. Interesting. Nested loops, where the first iteration of a loop uses one operation and the second uses two. The third uses three, and so on. That is, the number of operations is 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. In other words, this is the total number of operations that will be performed by the nested loop if the number of operations performed inside the loop increases by 1 with each iteration of the outer loop. This quantity also has an interesting history. What did that mean? That made no. I don't know about you guys, but I did not get any of that. I'm sorry. I'm really, truly sorry if I didn't. The scenario describes a classic example of nested loops leading to quadratic growth in operations. The sum of operations can be mathematically expressed as the sum of the first n integers. The sum of this formula derives from the arithmetic sum formula. In this case, of terms is n. The number of terms is n, right? The first term is 1 and the last term is n. So the number of operations total is n times n plus 1 divided by 2. Okay, now we're getting into some crazy stuff. Huh. In other words, okay, so in 1787, a German school teacher decided to keep his 9 and 10-year-old pupils occupied by adding up the integers from 1 to 100. But almost immediately, one of the children claimed to have the answer. The teacher was suspicious, for the student had only the answer on his slate, but the answer 5050 was correct, and the student Karl Gauss grew up to be one of the greatest mathematicians of his time. We presume that young Gauss used the following identity. For any integer n greater than or equal to 1, we have so you sum up all the integers, and then you add the value of... I'm not following this part right here. Why are we subtracting from n? To give it, we give two visual justifications of proposition 3.3 and figure 3.3. A visual justifications of proposition 3.3. Both illustrations visualize the identity in terms of the total area covered by n units, by n unit width rectangles with heights 1, 2, all the way to n. So we have heights 1 all the way to n. Then you have rectangles at each point up to n. Okay? In a linear form. In A, the rectangles are shown to cover a big triangle of area n squared divided by 2. Base n and height n plus n small triangles of area half area. Holy crap. This is getting annoying. You guys following this? So, I need to get this. This is a well-known result in mathematics and can be derived from using simple techniques. Here, an intuitive explanation. Write the sum in ascending order, right? If we reverse the order, oh, okay. That just means the reversed order. Okay, got you. So you start off at 100, 99, 98, so on all the way to 1. Okay, then you add the two equations. Which is 2 times s. Each pair sums to n plus 1, and there are n pairs. There's 100 pairs that all equal this. So solve for s. Okay, so it broke it down like this. So you sum, how it works is you sum all of the numbers going forward. Well, we know that all of the numbers in reverse order is the same sum as well. So that's 2s. And so you can basically plug in these equations, add the two equations together, So you have 2s is equal to the two equations blended. And so then, essentially, when you refactor this in, all of these parentheses equal to n plus 1. So 2, multiplied into is 2n minus 1 is equal to, with an n out front, 2n. Oh no, this is plus 2, not multiplied. So this isn't multiplication happening at all. So we would have to add 2 to the negative 1, giving us positive 1, n plus 1. Well, if every single one of those is the same, we have up to n of those. So we have, if n is our, if 100, if we're counting up to 100, well, we have 1 plus 2 plus 3 plus 4 plus 5 plus 6. That is like, summing all the way up to 100. Well, then you can do that in reverse order too. You can start at 100, take n minus 1, so that's 100 minus 1 is 99. So 100 plus 99, n minus 2, 98. 100 plus 99 plus 98. You sum all those. Well, and then we can combine those two equations to get 2s, refactor that down into n times n plus 1 is equal to 2s, solve for s, isolate it, and we get that. It's basically s is the sum of all, is the value of n, all the values up to n. Okay, got you. So big S is the sum of all integers up to n. Okay. Cool. Up to and including n. Okay, so it also includes n. The Vance, thanks so much for joining. I appreciate you stopping in for your time here. Anthony says the idea is that for a range of numbers from 1 up to n, or 1 to n, you can derive a formula to figure out the sum. Okay, gotcha. I remember this from discrete math, Jeremy says. Basically a trick to sum all numbers up to n. In other words, 10-year-old is a genius. Moving on. Yeah, a 10-year-old did this? How? That just makes me mad. Like, how? That is so dumb. Okay. Okay, the 7 okay, so the lesson to be learned from proposition 3.3 is that if we perform an algorithm with nested loops such that an operation in the inner loop increases by 1 each time, the total number of operations in the quadratic is the number of times n we perform the outer loop. To be fair, the number of operations is n squared divided by 2 plus n squared, or plus n divided by 2, and so on. And so this is just half of the operations that an algorithm uses n. Okay. Six, the cubic function and other polynomials. Continuing our discussion of functions that are powers of the input, we consider the cubic function. F of n is equal to n cubed. Which assigns an input value n to the product with itself 3 times. This function appears less frequently in the context of algorithm analysis than the constant linear and quadratic functions previously mentioned, but it does appear from time to time. Okay. I'll take this guy here, go function that when given the input value of that function which assigns, there you go, like that. There we go. Cool. Easy. Okay, so I completely forgot about that story. Holy nostalgia. Also, note that also note that literally any nested operations are going to be multiplied. So n cubed is just 3 nested time operations, whereas n squared is just 2 nested in time n time operations for 2 for loops. Gotcha. Yeah. You're just repeating a linear function twice over again inside of itself, or 3 times within itself over before you give an output. Exactly. Um, Polynomials. Okay, this is interesting. Most of the functions we have listed so far can be viewed as being part of a larger class of functions, the polynomials. A polynomial function that has the form of f of n is equal to a of 0, a sub 0 plus a sub 1, and a sub 2n squared, so on, where a, 0, a1, and d are constants called coefficients of the polynomial, and a d is not equal to 0. Integer d, which indicates the highest power of the polynomial, is called the degree of the polynomial. For example, the following functions are all polynomials. F of n is equal to 2 plus 5n plus n squared, 1 plus n squared, or plus n cubed, 1 n, okay, so all, yeah. Therefore, we could argue this book presents just 4 important functions used in algorithm analysis, but we will stick to saying that there are 7 since constant linear and quadratic functions are too important to be lumped in with other polynomials. Running times that are polynomials with small degrees are generally better than polynomial running times with large degrees. Yeah, so basically functions uh, are these are all most of the functions we've talked about so far are classified as polynomials, like he said, where you have some constant value being multiplied by the your inputs values, and then those can be squared up to some value of d, right? In increasing order, or in any order, not in some sort of order, up to the degree. So we'll say polynomials. And we'll say summations here. We'll see what I think. Okay. Summations. A notation that appears again and again in the analysis of data structures and algorithms is the summation. Yeah, I remember this, which defines as follows. For some integer a up to b, f sum all the values of a, right? Sum all the values up from there. So where a and b are integers and a is less than or equal to b, summations arise in data structure and algorithms analysis because the running times of loops naturally give rise to summations. Using a summation we can rewrite the formula of proposition 3.3 as summation from integer 1 up to n, I is equal to n times from that proposition, right? So if we have n of 100, right, we're saying we're summing from 1 to 100, and we can sub in that equation from above as big S, right here, is it? Oh, it's in our GPT. Um, Likewise, we can write a polynomial function of degree with coefficients a0 and ad as um, f of n is equal to a summation from integer 0 up to d from a of integer I times n squared, or to the power of I. With a degree of coefficients as, okay, so yeah, so you're summing, right, from right here. Oh no, from polynomials right here. You're just summing a coefficient multiplied by some value n, and those can continually increase in degree up to the polynomial's degree, right? The degree of the polynomial. So we're essentially just plugging in some coefficient for some coefficient at that integer value, right? Times n squared at that integer value. So it just represents the summation of polynomials up to the polynomial degree. Thus, the summation notation gives us a shorthand way of expressing sums in increasing terms that have a regular structure. Got you. So I'll come back, I think, tomorrow during review and put in some definitions here. I think that'll be good for the review. Exponential functions. Okay. A summation is just a for loop. Interesting. Okay, so Anthony says having two for loops that run n times that aren't nested would still give the algorithm an overall time complexity of just n, linear. Because are those for loops ran at the same time? Or how would that work? You know, would you have to add, would it be more of an addition, like a summation of the for loops rather than a multiplying, right? Instead of multiplying n times n for n squared, it's rather n plus n for the algorithm time. And is that so small for some cases that we don't necessarily care as much as n times n or n times n times n? You know, n plus n is probably a lot smaller in some cases for large data sets than n times n times n. So by having two for loops or three for loops together, three for loops that aren't nested, would it be just summing for the loops? Yeah, technically it would be n plus n, which reduces which reduces to n in big O. Okay, so I'm not exactly sure what big O means, but I'm sure we'll get there soon. Like like what Jeremy says, once you reach big O, I think you'll understand what really matters from this section. Shazi, I'm sorry I do not speak that language. I apologize, but I appreciate you coming and leaving a comment nonetheless. Thank you so much for coming in. Toast says, yeah, Goss just paired the first and last numbers and the second and last numbers and so on. He just paired the first and last numbers and the second and last numbers and so on. So he paired them as, how did he pair them? What do you mean? Like he added them together? So like 1 and 100 was 101 plus 99 and 2, it gives you 101. It gives you 101 times n over and over again, right? Yeah, so it just gives you n times n, which is the quadratic, right? Yeah. Yeah, technically it would be okay. Cool. Let's keep moving here, guys. Okay, the exponential function. Another function used in the analysis of algorithms is the exponential function. F of n is equal to b to the power of n. Stop doing that. Cool. Where b is a positive constant called the base, and the argument n is the exponent. That is, function f of n assigns the input argument n the value obtained by multiplying the base b itself by itself n times. As was the case with the logarithm function, the most common base for the exponential function in algorithm analysis is b equals 2. For example, an integer word containing n bits can represent all non-negative integers less than 2 to the power of n. For example, an integer word containing n bits can represent all the non-negative integers less than 2 to the power of n, right? Because you can represent binary into 1 or zeros. So you can represent that number times is the exponential of n, right? Okay, gotcha. We have a loop that starts by performing one operation and then doubles. We have a loop that starts by performing one operation and then doubles the number of operations performed with each iteration, and then the number of operations performed in the ninth operation is n2 to the power of the nth operation is n2 to the power of n. I'm stuttering all over the place, guys. We sometimes have other exponents besides n, however, hence it is useful for us to know a few handy rules for working with exponents. In particular, the following exponent rules are quite helpful. Given positive integers a, b, and c, we have, so if you're multiplying exponents outside of parentheses, you can just combine them and multiplying them together. If you're multiplying two of the same base values together with differing exponents, you can sum the exponents. If you're dividing exponents with the same base value, you can subtract the exponents. Yeah. We can extend the exponential functions to exponents that are fractions or real numbers, and we can extend the exponential function to exponents that are fractions or real numbers and to negative exponents as follows. Given a positive integer k, we define b1 divided by k, b the power of 1 divided by k to be the kth root of b. That is the number r such that r to the power of k equals b. R to the power of k equals b, or b divided power of 1 over k. For example, 25 to the power of 1/2 equals 5, since 5 squared is equal to 25. Okay. Okay, so this is just talk about exponents. We can further extend the exponential function to define b of x for any real number x by computing a series of numbers of the form b to the power of a divided by c for fractions a divided by c that get progressively closer and closer to x. Okay, this is getting real jargony, guys. This is getting like so jargony, and I think this all makes sense in the author's head, but I'm not sure if he really knows that he's losing an audience here. Oh boy. Anthony says, it would be nice if the book gave some examples of some code that demonstrated this runtime. Maybe you can look this up. Jeremy, you have reached the you really messed up territory where you say that your computer has the fan spin and the answer never comes, lol. Yeah, I think it's just trying to introduce these functions and then it's going to give some examples into things. But yeah, it's interesting. Maybe we should also take a stab at maybe some like videos or something to help these solidify these concepts even further. So the geometric sums. Suppose we have a loop for which each iteration takes a multiplicative factor longer than the previous one. This loop can be analyzed using the following proposition. Okay, geometric sums. Suppose we have a loop for which each iteration takes a multiplicative factor longer than the previous one. This loop can be analyzed using the following proposition. For any integer n greater than or equal to 0 and any real number a such that a is greater than 0 and a is not equal to 1, consider the summation. So n can't be 0 and a can't be 0 or 1. A has to be positive and not 1. Okay, so this just says that every loop is a multiplicative factor. Got you. Summations are shown in proposition 3.5 are called the geometric summations because each term is geometrically larger than the previous one if a is greater than 1. For example, everyone working in the computing should know that 1 plus 2 plus 4 plus 8 plus 2 to the power of n minus 1 for this is the largest integer that can be represented in binary notation using n bits. Well, working in computing should know. I did not know that, so we're screwed, boys. We're screwed. Comparing growth rates. To sum up, Table 3.1 shows in order each of the 7 common functions used in algorithm analysis. 1 constant, 1 logarithmic, log n, linear, n log n squared, n cubed, and a to the power of n for when a is greater than 1. So ideally, we would like data structure operations to run in times proportional to the constant or logarithm function. So we would like them to run proportional to the constant or log. And we would like our algorithms to run in linear or n log n time. Okay, so this graph, I wish they used color, but so we want our operations to run in times proportional to the constant or logarithmic functions. So the constant function represented in a diamond, right? Isn't just constant. Or logarithmic. So we want them to run fairly flat as we increase data sizes. But we would like our algorithms to run in linear or n log n time. So linear or n log n time. So you kind of want to be in this sweet spot, this like triangle here. Jeremy says the recursive Fibonacci algo is exponential because it has to call the function for the next 2 numbers. Recursion will be another fun brain strain down the road. Well, we'll get there, Jeremy. Thanks so much for the heads up. Anthony says, "Oh, look, a graph." Yeah, here we finally got a graph, like 5 pages later, right? Showing this. But so we want to resemble a fairly flat, line, and we want to have time that is pretty linear or logarithmic. Oh no, logarithmic, linear. I mean, sorry, linear in n log n. We want to have, and then constant or logarithmic is our proportional to, right? So we want to be fairly flat, and we want to have a good time. Okay, sounds good. Growth rates are the 7 fundamental functions used in algorithm analysis. Sorry, growth rates for the 7 functions. We use a base a equals 2 for the exponential function. The functions are plotted on a log-log chart to compare the growth rates primarily as slopes. Even so, the exponential function goes too fast to display all its values on the chart. So then the exponential function is just what god awful for algorithms. Like it's just like impossible to process large amounts of data with exponential functions. It just takes too much time. Now, what's like an example of like, I'm sure we'll see one, but like an exponential, just geometric sums, like you talked about, recursion Fibonacci algo has been exponential. So like when you go back and sum the previous two numbers, that's an exponential function. Okay, I'll go to the end of this page here, and I think I'll call it for tonight, boys, and we'll come back tomorrow, hopefully in a little bit more awake, and yeah, we'll tackle this. I know I know yesterday we did not get to the project again, but honestly, I'm really enjoying um, I'm really enjoying kind of learning and getting through the book, and I want to keep going, so that's why I've kind of prioritize this right now, but I need to this weekend for sure when we have more time after my work. It's just hard when you only have two hours, right, or so to stream. So this weekend we'll definitely grind away on projects. That's a factorial, Anthony says. Okay, so if the recursive Fibonacci algo is exponential. Okay, so it must be a different one that I'm thinking of. The ceiling and floor functions. One additional comment concerning the functions above is in order. When discussing logarithms, we noted that the value is generally not an integer, yet the running time of an algorithm is usually expressed by means of an integer quantity, such as the number of operations performed. Thus, the analysis of an algorithm may sometimes involve the use of floor functions and ceiling functions, which are defined respectively as follows: the absolute value, the largest integer less than or equal to x, or so you have a floor, which is the largest value less than or equal to x. So that's the ceiling is open, so you go up, and then this one is a floor where the smallest is integer greater than or equal to x. So if you have this notation where the ceiling is open, we want to go up, we want to round up. If you have this notation where the ceiling is closed, we have to push down into the floor. Okay, and go down. Oh, we're almost there, guys. We are so close. There it is at the bottom of my page here. The big O. Oh, I bet you my camera cover. If my camera covers the text, I'm sorry, guys. I completely didn't even think about that. Okay. Um, sorry, not factorial. It's 2 to the power of n, which this book didn't cover. It looks like 2 to the power of n. It did cover exponential. exponential with the common base of 2. Anthony, it's right here. So we'll say function where b is a posit constant say and n oh my gosh is the exponent most common base b it for exponent algorithms algorithm analysis is b equals 2. Okay. All right. Cool, you guys. I really appreciate you guys joining me today. I know I feel like I feel bad. I feel a little guilty that we haven't worked on the small business manager project because I know a lot of you really like watching that. It's kind of more definitely in my opinion probably more enjoyable to watch someone actually building a project than reading out of a textbook. But again, guys, this is an umbrella of knowledge that we have to soak in, and you know, if we want to take this seriously as a whole, we need to be willing to, you know, take in all avenues of knowledge. And in our current, you know, environment with products, with tech, with everything, with research, we are just heavily algorithm based, and with data structure, it's everywhere. It seems like so. This stuff might seem monotonous and maybe for some people boring, but it is pretty essential for the modern age today to know these things. So we got to stay true to it. We got to grind it out. It's just what we got to do. Sometimes we got to do stuff we don't want to do, but we're gonna, you know, I kind of actually want to do this. I want to learn it, and so it's fun. So yeah, I enjoy myself. But so tomorrow we're gonna dive into 3.3. We talked all about on 3.2. We were introduced to the 7 functions used in this book for data structures and algorithms. We were introduced to the constant function, where no matter the input size, we always are outputted the same value of time. The logarithm function, where we have some constant b or some constant base b, and it's basically how many times can we divide our um, our input size by the base in order to get to 1, and that provides the amount of time that elapsed for that function, or the output. We have a linear function which just represents the value of the input size itself, 1 to 1. So for every input size, we have that many outputs in terms of like time operations and such. I think so. For words, we have the n log n function, which you know, we had the log n above, but this itself multiplies every operation by the actual data sample size again. So this one does create some. I would like to better understand, get a better definition for this one maybe before we go, just to solidify this concept. So this one, a function that assigns to an input n the value of n times the log base 2 n, right? So that just this function grows a lot less rapidly than the quadratic, and therefore we quickly more, grows a lot more rapidly than the linear and a lot less than the quadratic, and therefore we would greatly prefer an algorithm with a running time that's proportional to the n log n than one with quadratic. So, do we have like an example, you guys, of an n log n function before we go? We really kind of honed in. We showed examples on the Desmos for it, but like this one talked about nested for nested loops. This one is triple nested loops. Um, this one was like talking about like some recursion. I think what we talked about in the chat was brought up recursion. Geometric sums was obviously an example, but for n log n, frequently an algorithm also represents operations that scale proportionally to the product of n. The product size of the input and the logarithm n. Here are some common examples. Sorting, so merging, sorting, dividing, conquer. Those seem like more specific examples, really, rather than kind of broad. I didn't really dive too deep into this one. The function assigns, that is, the function that assigns to an input n you search out merge sort is n log n. Okay. Got you. Well, I really appreciate that you guys stayed around for today's stream, and I really appreciate you guys participating. Like, truly, it helps make this learning process 10 times better. You guys have been awesome in supporting the channel. We are growing great. So, share it with other people that might be interested. Join the Discord. Let's get a community going. Let's keep learning, and eventually, as we gain more knowledge, we can maybe create like a community project, and we can get that steam rolling. I just feel like I want to get some more knowledge first before I kind of get people together working on something, because I don't want to be like the bottleneck behind things, but also sometimes you gotta sink to swim, right? So anyways, I'll see you guys tomorrow. Thanks so much for being here. Yeah, see you guys. Happy learning.